you would love to train your own transformers for NLP, and you ask yourself, hey, after PyTorch, is there an easy way how I can pre-train and fine-tune my transformers? Yes. On top of Keras, we have now Keras NLP. Hello community, let's have fun today. Last time I showed you Keras NLP and a lot of you asked me for a short introduction. Well, the best place I found was the official Keras guide. And as you can see here, we are here in Keras.io guide, Keras NLP getting started. And here we have an explanation on the left side and on the right side. There is a COLAB notebook, a free COLAB notebook. I have here the address of this notebook. I leave it in the description of this video so you just can go download it and follow and we do it together. Currently it is running because we have here everything is fine, beautiful. Because here we have the explanation and on this side we have the execution in a COLAB notebook. So here we go. What we do, we at first start what is the structure of this document. As you can see here, this is a guide and he goes from the most automated task. We have an inference task with a pre-trained classifier down to the most detailed task, build and train your own transformer from scratch. This is exactly what I showed you in my last two videos, either on PyTorch or on Keras. And now with this Keras NLP toolbox, we're gonna have a look again at the whole cycle of building transformers or using transformers as a pre-trained version. So here we go. First, as you can see here, upgrade Keras NLP, install TensorFlow, beautiful. Use mixed precision for optimal performance, beautiful. And then we start. Now, you have to understand there's a specific module structure to Keras NLP. And here we have our modules. User structure, yes, the following modules. Here we go. At first, we have a tokenizer. You know what a tokenizer is. We used it in my last videos. This is a tokenizer. Of course, we have a preprocessor. What it does, it converts strings to a dictionary of preprocessed tensors and consumed by a backbone, starting with the tokenization. Now you might ask, hey, what is a backbone and what is a task? Now, this is easy. A backbone here is, it converts the preprocessed tensors to the dense features. And a task is, it converts a string to a task-specific output, for example, a classification. Now, let's have a look at this in detail before we go on and we do the calculation here. As you can see, yes. So a classifier model is a complete model that we pre-trained, that we fine-tuned with a classification head on top of our BERT model. And this is it. And as you can see here, this is an end-to-end BERT model you can fine-tune for a classification task. This model attaches a classification head, and I showed you this in my last video. The classification head in the second phase after pre-training. We're now in the fine-tuning phase to our backbone. Mapping from the backbone outputs to logic outputs. Beautiful for classification task. And here we have two options. We can use the weights of the model, or we can say, no, thank you. So beautiful. Let's have a look at this. Oh yeah, the backbone. Before we start here, what is the backbone model? Now, this is just our BERT encoder stack. This is pure BERT without a fine-tuning head, without a pre-training head. This is just as you can have here. And look, this is the BERT model. Imagine instead of backbone, think about model. This is the BERT model. We have a vocabulary size. We have a number of layers. This is our transformer blocks. We have a number of attention heads. Those are the heads within each layer. We have a hidden dimension. This is the dimensionality that you get out This is the dimensionality of your vector embedding, 768, for example. You have an intermediate dimension. Yeah, this is the feed-forward network. This is default at 3072. Leave it at this. You have a dropout rate you can define. You have the maximum input sequence length. This is the number of token with the classification token included. That is the maximum sequence length. Otherwise, it will be truncated. The number of segments and whatever. Beautiful. So this is our classical BERT encoder stack. And they call it here the BERT backbone model. Great. And going back now to the classifier model, this is now a specific model for fine-tuning on a classification task. As you see, it takes as an input the backbone, so our BERT model, our pure BERT model without some classification head. The number of classes, we have, for example, a binary classification task. This is a friendly comment or this is an unfriendly comment, 2 classes. We can define the dropout threshold. And we can say, yeah, we want to have a preprocessor activated, yes or no. So this is more or less all there is to show you. Yeah, here, for example, I'm not going to show you the definition, but again, if you define your backbone model or your Keras BERT model, you have the vocabulary size for BERT typically is 30K. The number of layers, the smallest configuration is 12 layers. The number of attention head per layer is 12. The hidden dimension, or this what you have as an output, will be 768. Intermediate dimension will be 3000, and the maximum sequence length, now this is much too short, just 12 tokens is nonsense. But if you wanna see this here in Hugging Face, we have here the transformers. And if you go to the BERT configuration file, so that you see in PyTorch, it is absolutely the same. Here we have our Keras NLP toolbox in TensorFlow 2. And here on the right-hand side, we have here Hugging Face with the PyTorch BERT configuration file. And as you can see here, we have the same thing. Let's put it here, vocabulary, number of layers. Vocabulary size is 30K. The hidden size is, if here define the dimensionality of the encoder layers and the pooler layers, so input and output. So you get a 768 dimensional word embedding out of BERT. The number of hidden layers in the transformer encoder stack is 12, the same as in PyTorch and in TensorFlow 2. The number of attention heads for each attention layer in the transformer encoder stack, 12. The intermediate size is the dimensionality of the feed forward layer in the transformer encoder stack, 3000. You see absolutely the same. Here you can also define the hidden activation function as a GELU or ReLU or whatever you like. A hidden dropout probability, yes, and you have additional parameters here if you have here the BERT configuration file. But of course, this is a more in-depth configuration. But here we are looking really on a high-level API and a toolbox on top of Keras. So this is what we define our BERT model for. And then if we have, let's do this example here. If we have now the BERT classifier model, we have our backbone model, our BERT model. We have how many classes we want to classify. This is, for example, the number of classes, 4 classes, A, B, C, and D. We want to have a preprocessor, yes or no. And then we have our BERT classifier defined. We will now define a loss function and we can start and train it on our specific features. Beautiful. So this is about the nomenclatura. If you have now a backbone model, you know this is our normal BERT model. And if we have a task, this is now a full-fledged classifier BERT model ready to be fine-tuned on your data. Great. Okay, so this here is still running. Beautiful, beautiful. The data. Yes, what we have. Let's have a look here. The data, we will use some sentiment analysis of a movie review. And we have a binary classification task. Positive has label 1, negative has label 0. Beautiful. So we load this, as you can see here, from Stanford. Beautiful. We apply a Keras utility text dataset from directory. We import directly and create our training data, our test data. Yes, and then here we go now for the first example. Maybe I have to shift this a little bit that we can see it. Yes, this is much better. We have now here the beginner level. This is the highest level. This is the completely pre-trained, everything automated task. This is it. You see, Keras NLP, load a pre-trained model, BERT classifier. So this is already with the classification head. And we want some presets. So we want to load the weights of a pre-trained model. And we download it and we use the BERT tiny uncased model that has been trained on the Stanford training dataset. Great. So what we do, we say this is our classifier, do a prediction, and I give you a sentence. And I want to tell you, is this sentence positive or negative? So we download everything and then we get an answer. And the answer here is, yeah, we are here operating in TensorFlow with logits. You remember, logits are unnormalized probabilities, probability function. So if we have here the higher value in the logits, you normally is the indicator for you. So if you have minus and plus, you go with the result should be, if you would normalize it, with 1.543. This is the positive result. And this should indicate that this is a positive sentence, has a positive sentence connotation. Great. Do I have anywhere where 0 and 1 are defined? No, I have no way how the logits are defined. But let's go. They are ordered. So the first one is the label 0 and the second one is the label 1. Great. This was the data, this was the beginning, this was our classifier. So great. Now let's come back. This is our classifier. You see here we have exactly the same here in the theory. This is the preset. And we don't need an optimizer. Yes, yes, yes. Since we're not training the model, yes, of course we don't have to do this. So now we let go of the fully automized version and we say, hey, let's do some fine tuning. Now we want to be in command of the fine tuning task. We take a pre-trained BERT model and we do the fine tuning. This is great. So what we have, we load an available fine tuning. A custom classifier can improve the performance. We want to predict the review sentiment data. Yes, 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 yes. So what we do, let's have a look in theory and then we see how we compile it. You see it's absolutely the same text. So here we have a classifier and we load from a pre-trained BERT model. And I have no idea, for me it's a black box. I don't know the BERT tiny English uncased model, how intense it was trained, on what data it was trained. Whenever you have from preset or from pre-trained, this is a black box model for me. I just know it is there. I can use it out of the box, but it's a little bit of a blind flight for me. But let's use it. We have it. We say the number of classes is a binary classification task. We have here the classifier. And as I told you, we want to fine tune now it manually if you want. So great. What we have now, of course, to compile with our loss function. We have a sparse categorical cross entropy from logit is true. Don't know if you remember this. If you go here in the TensorFlow 2 API, we have here our Keras losses, the sparse categorical cross entropy. And if you look at the definition, we say we use this cross entropy loss function where there are 2 or more labeled classes. And we expect labels to be provided as integers. If you want to provide the label as a one-hot representation, we use the classical categorical cross entropy. But since we have here our logits, we have our integer from minus infinity to plus infinity. We have a logit representation. So therefore, we use here our sparse categorical cross entropy for 2 or more classes. Beautiful. Now you understand this. We have an Adam optimizer. And we have very simply, we have now the training of our classifier on our data set. We have a validation data set, and the number of epoch is 1. Wow. This is really something, hey? Number of epoch is 1. Yes. Okay. It's just for demonstration purposes. You see, it's running through, and what you do, you have here more or less the automatization from a preset model working for you. Beautiful. You do not have to pre-train anything, but it is kind of a black box for me. Next step. Fine-tuning with a user-controlled pre-processing. Okay, now we come closer to the main topic. If you have large data sets, examples can be pre-processed in advance and saved to disk or pre-processed by a separate worker pool. This is great. That's what we're gonna do. Separate pre-processing from the same preset. And we will do this with a matching preprocessor. Yes, of course. And we have here again our beautiful TensorFlow.data command that I already showed you, where we do the perfect optimization, the configuration of the CPU to the GPU processing so that every worker is optimally tuned. So what we have here a BERT processor from a preset. We have a sequence length of 512 tokens, and then we have our training data set, our test data set. And then we have our BERT classifier again, and we compile it and train it now in 3 epochs. Yeah, there's nothing specific to it. Here is the code. We just ran 3 epochs, and beautiful. What is here the loss and what is the accuracy? Where are we? 86, 87%. Validation accuracy has only increased to 88%. This is both a function of the small size of our data set and our model. To exceed 90% accuracy, we have to try larger models like the BERT base model with 12 layers. This is clear because we have here the BERT tiny model, so the really, really tiny model. So this is the explanation that they say, okay, it is stuck below 90%, and to exceed 90%, please use BERT base or BERT large model. So the larger models, well, of course. Okay, next step. We do now a custom pre-processing. Yeah, now we are coming to the interesting part. In case where custom pre-processing is required, we offer direct access to the tokenizer. Finally, we come to the tokenizer that map raw strings to token. So this is what we do. Let's have a look here in theory, and the execution, as you can see, is already done here on the right-hand side. So what we say, we have a BERT tokenizer. Yippee! But we have it already from some preset, some pre-trained BERT models. So we are still looking kind of in a black box here, but we have now our BERT tokenizer. And we tokenize our sentences, for example. We have here a packer, we have a tokenization ID, we have a separation token ID, we have defined a sequence length, beautiful. We define a function pre-processor like last time where I showed you we have the token IDs, the segment ID, and the padding mask. And then we just use here the training of the pre-processed training data and the test data. Beautiful. This is done. We executed this. Yes, 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 yes. Okay, and then we come finally, here we go, fine-tuning a custom model. Just look, where are we with our execution? Is everything fine? Everything, yeah, beautiful. We are just in the demonstration mode, great. But where are we in the execution? Where are we currently waiting? Just to have an idea, where are we? Where are we? Oh yeah, okay. Model compile, 3. Okay, so not bad. Already at the last element, advanced, where's our advanced little something here? Expert, no, advanced, here we go. So here we go. Oops, no, this was not my intention. Now, fine-tune a custom model. Here we go. Now we can really touch the model. We can manipulate the model. Here we go. As I told you, we have here a backbone model, and we have here now the task to be defined. So let's look what we have here. We have a BERT preprocessor from a preset, and it is still the BERT tiny preset. Okay. And then we have here our backbone model. Hey, welcome. The first time we have now the BERT model. And it's already a black box model because we say from preset BERT tiny. So we have a pre-trained BERT model, but at least we see for the first time our BERT model. Great. So you have your training data pre-processed, you have your test data pre-processed. And we have our backbone, yes, the input. We have the sequence output, yeah, and for a range, yes, we do, as I showed you last time, our transformer encoder stack. So we say here, we built two transformer layers, two transformer blocks with our beautiful command from the Keras NLP Toolbox, layers.transformerEncoder. It builds a complete encoder layer. We say the number of heads in this layer, attention head is 2. The intermediate dimension is quite reduced, 512, okay. The dropout rate is set to 0.0, beautiful. And then what? They use the CLS token output to classify it. Now, this is an old method. Please do not use this. I know it was used in the old times, so about 1 year ago, 1.5 years ago. And the idea is simple. The idea was, if I have a sentence, and for each sentence, or for each word in this sentence, I have sub-word tokens. And instead of taking all the representation of the embedding of those tokens, because I have self-attention in this sentence, I can use only the first token to classify the complete sentence, the output. It has been shown that this is not the best, not the optimal approach. So, okay, we do it because this is here a demonstration notebook from Keras, but please do not use this anymore in 2023. As I showed you in my last video, we have better options. Please check out my last video. But okay, let's say this is it for the moment. So we have our model, as I showed you in my last video, with our input defined, our output defined. We compile it with our cross entropy, with our Adam optimizer. And then we simply say, okay, let's train this model on 3 epochs. And since we say, okay, model summary, we get an idea how our model is constructed. And again, as in our last video, we have here our input layers. Then we have here the BERT model in itself with the trainable parameters, as you can see it. And then we have here a transformer encoder layer, a second layer, and then we simply have a dense layer, because we have to have a classification task, a binary classification task with an activation function. Beautiful. So as you might see, okay, show me the execution. This is exactly as I showed you here, our CLS token, our classification token output to classify the whole thing. Please don't do this. We have here again, we have here the number of total parameters, and it just ran our 3 epochs. Beautiful. This is great. And now finally we're here, we're pre-training a BERT model. Now we come to the most important thing. We have already done this in my last video, but since it's an expert level, hey, why not have a look at this? System is already done, so great. Do you have access to a large unlabeled dataset in your domain? And as I showed you, you're working in biotechnology, you're working in the pharma sector. You have large unlabeled dataset, thousands of pages of your customer experience or your research projects. Then there are sound the same size as a trained popular BERT. You have BERT or Roberta, the improved method, or GPT-2, GPT-3. And if so, might ban it for some domain-specific pre-training for your own backbone models, so for your own BERT models or your own Roberta models. And we have the domain-specific pre-training. This is the most important wording. And should be more or less exactly like in my last video. I'll leave you the link to my last video here. But let's do it. So we know we're using here Keras natural language processing library. We have the backbone, we have the tokenizer, and we pre-train now a BERT model using the movie review text. As I showed you also in my last video, we skipped the next sentence prediction task, the loss. You remember the original BERT model has been trained on the mask language model and on NSP, but it was shown later on that the NSP, that the next sentence prediction pre-training, does not bring so much benefit, and it takes a lot of compute resources for the pre-training step of our BERT model. So we forget NSP and we only do the mask language model mask generator layer for the pre-training as shown to you in my last video. So, and here we go. We take here a BERT preprocessor again from preset. Okay, this is not really done completely from scratch, but okay. We have our packer, we have our tokenizer. And then here, as I showed you, now we pre-trained the model on our mask language model mask generator. Here we go. And this is it. This is the layer that we put on top of our BERT model with our 12 layers and whatever we defined. And we have to find again the vocabulary size, the mask selection rate, 25%, put it on 18%, 21%, whatever you like, the length, the mask token IDs that we have, the padding, the separation, the classification, tokenizer, the special tokens, great. Then we define, of course, the pre-processing. We have our inputs. We have our segment IDs, padding, mask position. We need exactly like in the video I showed you last time. And then we have simply our training data and our test data. And this is it. Beautiful. And then let's go here in the theory. We have now our BERT model. Yeah, here we are. BERT model, BERT backbone. So here we can now define the number of layers in our BERT model. We can define the number of heads in each transformer block. We can define the number of the hidden dimension, the output dimension. So we only get a 128-dimensional embedding of our words. This is not enough, but for demonstration purposes, okay? And the intermediate dimension of our feed-forward network is instead of 3072, is reduced to 500. Not enough for the real case, but for demonstration, okay. So here we go. This is our BERT model. On top of our BERT model, we now put another layer, and this is our mask language model head. Beautiful. And now we have here our pre-training. Yeah, this is the special tokens. Yes, yes, yes. You say, where's our model? Here's our model. Keras model with our input, with our output. And then we start here to compile it with our special sparse categorical cross entropy from logit is true. We have a non-normalized logit. Otherwise, we would have a probability distribution. We use our Atom optimizer. JIT compile is true. You know why this is important. And then we simply pre-train our BERT model on our pre-training data set, on our validation data set. And we use a number of epochs for 3. So let's have a look. This is the code executed. You see this is absolutely the same as I just told you. And here we are now. Oops, where are we? Again, this is now our BERT model. The numbers of layer, the number of attention head. Yes, yes, yes. Here again, the model. Here we do the compile with our cross entropy function, with our Atom optimizer. And then we say, let's train the model on this particular configuration. And as you can see, I have another where I am, model summary. Here's a model summary. So we gotta have a look at the architecture of our BERT model. So we have our input layers. Then we have our BERT model in itself with our number of layers and the number of attachment head in each layer and. This is the BERT model. And then on top, we put one additional layer, and this is the mask language model head only for the pre-training. When we do the fine-tuning, we will put this layer away and we will have our classification layer. And as you can see, beautiful. This is the number of parameters. This is great. We have our 3 epochs done, and we have now a model, and this is it. Hey, wow! There's another part. My goodness, this will be a long video. Build and train your own transformer from scratch. This is exactly our last video, what I showed you in my last video. But now, since it's here officially, let's have a look how it differs. Okay, I tell you something. We look now at the original video. So, we have now our custom vocabulary. Finally, we can build our own tokenizer. Yes, we do not have to say load a BERT tokenizer from a pre-trained model. No, here we go. So we have here our tokenizer compute word piece vocabulary and use in our toolbox, Keras NLP toolbox, TensorFlow 2. We look at the tokenizer, and then we use a BERT specific tokenizer, the word piece tokenizer. And we say, okay, lowercase is true, strip the accents, the French accent, strip it away, beautiful. And our out of vocabulary token, our unknown token is defined with UNK. This is our special token we define in the tokenizer. And we have our packer for end, start, end, and padding. The sequence length is 512. Beautiful. We have our training data set, our validation data set. You can see it's executed. And then we design a tiny transformer. Okay. Input, yes, is integer 32. Okay, output is now, again, like last time I showed you. We had the very first layer is the token and the position embedding layer, where we have a vocabulary size, a sequence length 512, 768 or 1000, whatever you like, embedding dimension. And then we have our output, and here we have now our specific layer, the TransformerEncoder layer. This is great. We just have one layer. What? Yeah, visibly. Okay, the number of heads, the intermediate dimension, this is much too small for the real world case, but we are here just in the demonstration phase. Oh yeah, and again, they use just the start token, the special token to classify everything. Please, we are in 2023. Follow my last video. This is a oversimplification that does not deliver the best available results currently to our knowledge. And then we build our model, our inputs and outputs, and we have a model summary. Yes, you know everything here already. And as you can see, we really have here the TransformerEncoder. Great. Then we have a dense layer and our activation function for a classification task, for a binary classification task. Token and position embedding, our TransformerEncoder stack, and our dense layer for the classification task. And then easy, we compile it again, sparse categorical cross entropy from logic is true, or you normalize it before, then you can get rid of this, our atom optimizers, and we train our model. We have our training data set, our validation data set, the number of epochs is 3. And as you can see, I just ran all 3 epochs here on those 3 column notebook, and it is about 150 seconds. Beautiful. And we get a categorical accuracy 90% and sparse 88%. So, okay. So to see and exceed 90%, we need a bigger model, not BERT base, but not the BERT tiny, but BERT base. So beautiful. So we ran through all of the introduction to the official introduction to Keras NLP toolset. You do not have to know anything anymore about TensorFlow 2, except you're really a hardcore programmer, a coder who wants to have a deep dive in the code, then of course. Otherwise, we have Keras, and on top of Keras, we have Keras NLP. We did everything. We have a perfect introduction here, the official notebook from Keras. We built and trained our own transformer from scratch, like exactly I showed you now in my last video. But now we have successfully performed the introduction course by Keras for Keras NLP. I hope you enjoyed it a little bit. Again, as I told you, here is the link to the COLAB notebook, and you can run it yourself. Those are the tasks we performed from the most automated, completely pre-trained model. This is more or less a black box for us, down to where we build everything, our own transformer from scratch for our domain-specific knowledge data. I say thank you for listening. Thank you for watching. I hope you enjoyed it. Thank you for the official author, Bishop. It was created at end of December 2022, so quite recent notebook. I hope you have fun with Keras NLP, and I see you in my next video.